All right, in this video we are going to talk about solutions. So we're going to talk about what a solution is and its parts, and then how a solution forms, and the things that can change the rate or how fast a solution forms. And then of course we'll have a little discussion about solubility. So the definition of a solution is it's a homogeneous mixture. And it's made when one substance dissolves into another substance. So what do I mean by homogeneous mixture? So a homogeneous mixture is a mixture that's evenly mixed. So for example, this pitcher of Kool-Aid right here, when I put the Kool-Aid powder into the water and I mix it around, it mixes evenly so that when I pour a glass or another glass or another glass, all of the glasses of Kool-Aid taste the same because they're evenly mixed. There are two parts to every solution. So the first part of a solution is the solvent. Solvent is the part of the solution that does the dissolving, and the solute is the part that gets dissolved. So in our Kool-Aid example, the solvent is going to be water, and the solute is going to be the Kool-Aid powder, including the sugar and all of that. So you should know that usually there's only one solvent, but sometimes there's more than one solute. And the solute is usually, the solvent is usually the component that there is more of. So in our, again, Kool-Aid example, there's usually more water than there is Kool-Aid. That makes the water the solvent. And solutions come in a lot of different just varieties, I guess. So I underlined here, I'm going to do a bunch of examples, and all of the things that I underlined are going to be the solvent, which makes the things that I listed first the solutes. So you can have a solution where your solute is a solid and you dissolve it in a liquid. So for example, you could have our Kool-Aid mixture, or maybe salt dissolved in water, or things like that. You can also have solids dissolved in other solids. Examples of that would be any metal alloy, like bronze. Bronze is a metal alloy that's made of 88% copper and tin. So the other 12% would be tin, and that makes the copper your solvent and the tin your solute. You could have a gas dissolved in a liquid, like soda, Coca-Cola, Pepsi, things like that. The gas would, of course, be your carbon dioxide, and your water is your solvent. Okay, examples of a gas dissolved in a liquid, or sorry, a gas dissolved in a gas. That would be like our air. Our air is mostly about 79% nitrogen, and you have about 20% oxygen, and the remaining 1% is just other gases. And of course that makes the nitrogen the solvent because there's more of it. And then a solution of, say, a liquid dissolved in a liquid, that could be something like rubbing alcohol. When you go to the grocery store and you buy a bottle of rubbing alcohol, what you have is about 70% isopropyl alcohol and about 30% water. So that makes, of course, your 70%, the alcohol, is your solvent. In this class, we are going to mostly focus on aqueous solutions. So that's going to be the kind of solutions that we're going to deal with. And of course, an aqueous solution, if you remember, is water is your solvent, is acting as your solvent. And we can have various solutes. Some of them will be solids, some will be gases, and some will be liquids. So you might be wondering why some solutes dissolve into some solvents but not into others. So you can think of maybe paint or oil, how that doesn't dissolve into water, or like fingernail polish, but you can get fingernail polish off with fingernail polish remover, acetone, or you can get paint out of things with paint thinner, or oil, you can dissolve oil into things like acetone or turpentine as well. Why is that? Well, you actually already know the answer. And it has to do with intermolecular forces. Remember, intermolecular forces are the forces of attraction between molecules. So some molecules are attracted to other molecules through intermolecular forces. And if they're attracted to one another, then they're going to dissolve into each other. So if you remember, we talked about this before, this term like dissolves like. And that's where polar solutes will dissolve into polar solvents, or ionic solutes will dissolve into polar solvents, and then nonpolar solutes tend to dissolve into nonpolar solvents. So if you're trying to dissolve something like wax out of something, you're not going to get it with water, because wax molecules aren't interested or attracted to water molecules, and vice versa. Water is not attracted to wax. And so they're not going to mix or be miscible. So it wouldn't, water wouldn't dissolve wax. So if you want to get wax out of something, you've got to use a solvent that would work. Carbon tetrachloride is a solvent that would get wax out of something. So how does a solution form? Well, that's called solvation. So solvation is the name of the process where solvent particles will surround a solute or surround solute particles and carry them off into solution and mix evenly. Or a shorter way of saying that, it's the process of dissolving. For something ionic, when it dissolves, so here's, say, a chunk or a crystal of salt made of sodium and chloride ions. The solvent, which in this case would be water, would come in and just start plucking these ions away from each other and carrying them off into solution. And you'll notice that the positively charged sodium ions would be attracted to the negative pole on the water, whereas the negatively charged chloride ion would be attracted to the positives on the water molecule. So that's how something ionic would dissolve, and you'll notice that the ions end up separate from each other. For something like sugar, this would be like a sugar molecule. Sugar's not made of ions. And so you'll notice that the molecule itself doesn't actually break apart into carbons, hydrogens, and oxygens. It stays a full molecule, and of course, those molecules will just be plucked off the larger sugar crystal and carried away. So it's important that you understand that ionic solutes, when they dissolve, that compound, the ionic compound, breaks into individual ions inside the solution. So sodium chloride will break into sodium ions and chloride ions that then are surrounded by water molecules. And a polar covalent solute, when it dissolves into water, the compound remains intact, meaning that the molecule doesn't break into individual atoms. They stay whole molecules, but the molecules will then separate from each other. So we should talk about the factors that affect how fast or the rate of this process of solvation. And you already know this stuff. If you want to get something to dissolve faster, you could do a number of things. So the temperature of the solution would actually have an effect on how fast something dissolves. You already know this, but solids and liquids tend to dissolve faster in warmer solutions. So when you put a teaspoon of sugar into cold tea versus hot tea, it'll dissolve a lot faster in the hot tea. But what you might not be aware of is that gases, if they're your solute, they tend to dissolve faster in colder solutions. So you can think about cold soda versus warm soda. Cold soda is fizzier, or rather, it keeps its carbonation faster or longer than warm soda. It doesn't go flat as fast. That's why we put soda in the fridge, to keep it cold, so it doesn't go flat as quickly. Also, it just tastes better cold. The second factor that will increase or affect the rate of solvation is stirring or shaking. So, if you put a teaspoon of sugar into the bottom of a cup of water and walk away, you come back, it will have dissolved. It just takes a lot longer. So if you want it to happen quicker, you stir it. And the reason why is because it actually increases the contact between the solute and the solvent particles so that they just are attracted sooner. And then the last thing is the size of the solute pieces. So here we have, say, sugar cubes versus powdered sugar. Powdered sugar, or sugar cubes, if you were to look at them up close, are a whole bunch of sugar molecules. And for those to dissolve, the water molecule has to come in and pluck the individual sugar molecules off and carry them into solution. The problem that you face with a sugar cube is it's going to dissolve a lot slower because these molecules on the outside have to be plucked and pulled away before water molecules can get to the molecules on the inside. So if you want to increase the rate of dissolving, you can take your sugar and make it, crush it so that you're already separating those individual molecules of sugar so the water molecules can get in between them a lot faster to carry them away into solution. This is also called increasing surface area. You'll hear me talk about how you can increase the surface area of a solute. And how do you do that? You crush the solute into smaller chunks. So the last thing that we're going to discuss is this idea of solubility. So the definition of solubility is the maximum amount of solute that will dissolve into a solvent at a specific temperature. And it's usually given as a measurement of the number of grams of solute per 100 grams of solvent. And oftentimes you'll be able to look up the solubility of solvents on something called a solubility curve. All right, so this is a solubility curve. So this just shows the solubility. So for example, I can pick something like potassium chloride. This line shows the solubility of potassium chloride at a bunch of different temperatures. And of course, the solubility is the number of grams of sodium chloride in 100 grams of water. So if I wanted to know the solubility of sodium chloride at 60 degrees Celsius, then all I'd have to do is follow 60 degrees Celsius up to the potassium chloride line, and then of course follow the potassium chloride line over to my solubility, or to the y-axis, and it would show me that at 60 degrees Celsius I could dissolve about 45, so we're right about here, grams of potassium chloride for every 100 grams of water. And there are 3 levels of what we call saturation. So for solutions, the first level of saturation, and a level of saturation, is a saturated solution. And that is a solution where the solute is dissolved until you can't dissolve anymore. So you can keep adding extra solute to your solvent, but it's not going to go into solution. It'll just sink to the bottom. That's a saturated solution. It's at capacity. It's not going to dissolve any more solute. Then there are unsaturated solutions. So an unsaturated solution is a solution with less solute than a saturated solution. So you can dissolve more. So you can just put another teaspoon of sugar in that cup of tea and you know that it's going to dissolve into it. It's not going to just stop dissolving the sugar and the sugar will sink to the bottom. It can hold more. And another type of saturation is a supersaturated solution. So a supersaturated solution is a solution where you have more solute dissolved in your solution than you should be able to dissolve at that particular temperature. So there's more solute than the solution should be able to hold. Now, a supersaturated solution is kind of fun because this is how soda pop is made. So, when you open the lid on a soda and it fizzes over, that's because the carbon dioxide that's dissolved in the water of the soda is supersaturated. it doesn't want to be dissolved in there. There's more dissolved in the water or in the liquid of the soda than there should be. So when you release the pressure by opening that lid, it actually releases that extra solute. In this case, because if it's a gas, it'll fizz out. Supersaturated solutions that have a solid dissolved in water or a solid dissolved in a liquid, tend to be done this way. What you do is you put in your solvent, your solute, till you saturate the solution. So you have extra sitting on the bottom. So say at 25 degrees Celsius, room temperature. Then you heat it up, and that causes that extra undissolved solute to dissolve into the solution because you're at a higher temperature. And then you cool it slowly so that it maintains the solute that it shouldn't. So remember, at 25 degrees Celsius, you should have that extra solute at the bottom, but because you supersaturated it, it stays dissolved. Now, the supersaturated solution is very unstable. If I were to take just one crystal of that solute and drop it in there, that crystal will sink to the bottom, and all of these crystals or all of these solutes would start to glom onto it, and it would start to crystallize. So it's pretty cool. I'll actually demonstrate a supersaturated solution in class. And just because it's cool, supersaturated solution is what a cloud is. A cloud is actually a whole bunch of little dust particles, and water molecules have kind of stuck to the dust particles and formed a cloud. And I don't know if you've ever heard of cloud seeding, but it's a really interesting process where we spray silver iodide into the clouds. And the silver iodide acts like this crystal did when I dropped it into the solution, and then all the little dissolved solute sort of gloms onto it and crystallizes out. Well, the same is true with the silver iodide. You spray those little silver iodide into the cloud, and water molecules will start to glom onto it, and then they get really heavy, and then they fall or precipitate out as rain or snow. It's called cloud seeding. All right, and finally, let's talk about factors that would affect the solubility of a solvent. So remember our solubility curve. You know that you increase the temperature of a solution, and that's going to make solid solutes more soluble. So that means more grams of solute would be capable of dissolving per gram of solvent. So if you look at your solubility curve, you can see that general trend that all of these solid solutes are, their solubility is up. It increases as you go up in temperature. And then you'll notice something like this cerium sulfate has a decrease because it's an odd one. But for the most part, you'll see an increase in the solubility of solid solutes with temperature. Now, gases are different. When you increase the temperature, you get less gases dissolving. So a decrease in temperature tends to make gases more soluble. So some fish would prefer to live in cold water than warm lakes, because there's more oxygen dissolved in a cold lake than there is in a warm lake. And of course, another example is warm soda versus cold soda. Cold soda tends to not fizz as much as warm soda because it actually holds that carbon dioxide better than the warm soda. Warm soda, gases don't like to dissolve into warm soda, so they tend to fizz out. All right, and last but not least, pressure. How does pressure affect solutes? Well, pressure, first of all, only affects gaseous solutes. And so you can think of, again, soda. How do they get those carbon dioxide molecules into the solution? They pressurize it, and that just literally pushes the gas molecules into the solution and keeps them there. And then, of course, if it's a soda, when you open up that soda, you are, taking the pressure off, releasing the pressure, and then those gas molecules undissolve, and that's why a soda fizzes when you open it. So that is the end of my presentation on solution chemistry.